Hello and welcome to a new video. This is KStevMath, and today I'm going to be talking about the Pythagorean Theorem. Now, it says on here Precalculus Lesson A because this is intended to be helpful to some students that I'm working with through a pre-calculus course that uses the Math UC curriculum. But really, if you just need help on the Pythagorean Theorem, I'm sure that this video would help you with that no matter what class you're in. You could be in geometry or an algebra class going over the Pythagorean Theorem, and likely this will help you out as well. Now, if you would like to be able to take notes while you are using this video, you can go over to my website. There's a link in the description, and there you can find a free notes page that you can download, and it'll be especially helpful in a lesson like this where there are triangles that you may get frustrated if you have to draw those triangles yourself. Not that you have to draw them yourself if you're taking notes, but when you're taking notes, it's really helpful to have the original problem written down and to work it out so that you, as you're looking back, know what's going on. So downloading that notes page and printing it off would be a great way to have those diagrams available without having to draw them yourself. Anyway, let's get started with what is the Pythagorean Theorem. Alright, so our first question that we'd want to ask ourselves is, what is the Pythagorean Theorem? Arguably, this is the most well-known theorem for math, because I'm just thinking if you were to randomly ask people on the street if they knew any math theorems, this would be most likely the one that they could come up with. Or if you said, hey, have you ever heard of the Pythagorean Theorem, to just somebody you're randomly talking to, they'd be like, oh yeah, I've totally heard of it. That doesn't mean that they would know how to solve a problem with it, but I think most people have heard of it and remember it from their time in school. What I really like about it is it's also a fairly straightforward theorem. So all that's required to use the Pythagorean Theorem is that you have a right triangle. And in this right triangle, we are going to kind of define two parts to that right triangle. If you remember from geometry, triangles have three sides and three angles. And the Pythagorean Theorem, we need a right triangle, which means that one of the three angles needs to be exactly 90 degrees. That means that the other two angles, since all three angles have to add up to 180 degrees, that means the other two angles have to add up to be 90, which is kind of an interesting and cool fact about right triangles. So we define the sides of a right triangle as legs and a hypotenuse. So the legs are basically the sides that are not the hypotenuse. The hypotenuse is the side that is directly across from the right angle, and it is also the side that ends up being the longest, because in triangles there's this cool relationship where the biggest angle and the biggest side are across from each other, and the smallest angle and the smallest side are across from each other. And so that means that as we are looking at a right triangle, that right angle has to be the biggest angle. So the side across from it, we've named a special name, the hypotenuse. So the other two sides then are called legs. I don't know why, but that's what they're called. So this would be true. I have a right triangle here. You can see like somewhere around my head. I don't know yet which side it'll be on. I won't know that until later. But A and B are the legs, and C is the hypotenuse. And so if this is a right triangle, then it has to be true that A squared plus B squared equals C squared. And the opposite of this is also true, that if you have a triangle and you don't know if it's the right triangle, if you plug it in and A squared plus B squared equals C squared, so the two smaller sides, you square them and add them together, and you set it equal to the third side, the biggest side, if that relationship is true, that A squared plus B squared equals C squared, then you know that that has to be a right triangle. So we're going to do some examples of this both directions. We're going to both be looking for missing sides using the Pythagorean Theorem, and then we're also going to have some side links and test out to see if they form a right triangle or not. It will be helpful for you to have a calculator handy, just for squaring things, adding things, and we will talk about what we do with square roots, that there are two options. We can either simplify our square root if we end up with a square root, or we can find the decimal. And so either case, actually, a calculator will help us do that. So if you have not already grabbed your calculator, go for it. And if you are in Algebra 2 or Precalculus or above, let me recommend to you a TI-84 plus CE graphing calculator. I've got a video of some things you can do with that that'll pop up, and I'll put a link into the description with that you can go to Amazon and buy one of those calculators. It is an affiliate link, so if you go there you buy it, then I get something out of it, and you also get a really cool calculator out of it for buying. Like you buy a cool calculator, so good for you. So anyway, let's get to these examples. Alright, we've got a triangle here, and we are going to find the missing side. And so one of the things we need to make sure we understand is what are the legs and what are the hypotenuse, although this figure is labeled helpfully with an H, so you wouldn't think that they'd accidentally label an H on the side that's not the hypotenuse. That would be bad. So we are looking for the hypotenuse in this case. That means that our other two legs are A and B if we're thinking about the Pythagorean theorem. And so if I'm filling in A squared plus B squared equals C squared, then my sides here would be A and B, both of those would be 2, and H would be C. So I'm just going to fill those into, this is basically a formula. So 2 squared plus 2 squared equals H squared. So in order to solve this, we need to square each of these 2's. We square them first. Exponents come before addition in order of operations. So 2 squared is 4, and 2 squared again is also 4. Now we can add 4 plus 4 is 8. And then 8 equals H squared, but we just want H. So to get rid of the squared, we square root both sides. Now when we are solving an equation in math and we use the square root, usually we put a plus or minus sign in front to show that there are 2 answers. But because what we're talking about here are side lengths, it does not actually make sense for our side length here for a hypotenuse to be negative. So we're choosing to ignore the fact that there is a positive and negative answer here, and we're just choosing to use the positive number that we get from positive square root of 8. So like I said, there's 2 ways we can write our answer. We can simplify the square root, which the majority of math teachers would prefer you do it this way, but we also can type into our calculator and get an answer for it as well. So I told you to get your calculator, but I did not get my calculator, but that's okay. I'll do that real quick. So the square root of 8 as a decimal is, we're going to round to 2 decimal places, so 2.83. If you're ever wondering what to round to and something doesn't specify, rounding to 2 or 3 decimal places is usually sufficient, depending on kind of what you're doing. Very rarely would we just round to the nearest whole number unless we were told to, or if we knew that we were talking about something that makes sense more as a whole number than as a decimal. So our decimal answer to this is 2.83. To simplify the square root of 8, what that means is that we're trying to get the smallest number inside of the square root as possible, and we do that by taking out any perfect squares that are inside of 8. So we think about what multiplies together to get 8, which is 4 and 2, and we think, okay, if I split this up, can I take the square root of 4, or can I take the square root of 2? I can take the square root of 4, that gives me 2, but this part, this square root of 2, I can't actually square root that, it would just give me a decimal, and it's a prime number, so there's not any other numbers inside of the square root of 2 that I could switch that to, that would make it so I could simplify. So the square root of 8 simplified is 2 square roots of 2. So that's the 2 versions of our answer here. And if you have your calculator and you want to try it, type in 2 times square root of 2, it should give you that same decimal that we got, the 2.83, that was from the square root of 8. That's how you can, that's a way that you can actually check yourself to see if you have simplified the square root correctly. Alright, another one that looks a lot similar. We have this time a bigger triangle. The right angle is up here at the top. We've got hypotenuse labeled across the way. We're trying to find the hypotenuse. So it doesn't matter which of these you label A and B, but 6 and 9 are our legs, so they are A and B, and then our hypotenuse C equals H. So we want to do something like 6 squared plus 9 squared equals c squared, or h squared. It doesn't matter, actually. I feel like it doesn't actually matter which one you put. Since I labeled h on the triangle, I should put h. But if you accidentally put c, that's probably fine too. So let's see, 6 squared is 36, and 9 squared is 81. And then we will add these numbers together. So 36 plus 81 gives us 117, which for better, nope, is not a prime number. I was going to say I think that's a prime number, but if I add these digits together, 1, 1, and 7, I get 9. 9 is divisible by 3, which means 117 is divisible by 3. What do I get if I divide this by 3? I get 39, and then 39 is 3 and 13. So that means that I can actually write 117 as 9 times 13. And that's helpful because we can take the square root of 9 and get 3, which means this simplifies to be 3 square roots of 13. The other way to write this is to write the decimal approximation. And so, like we did just a second ago, we'd get out our calculator and we would say, okay, what is square root of 117? And really, it might have been better for us to do this in the other order, to square root it first, because every now and then our answer will be a perfect square. And if you don't have perfect squares memorized, that's fine. But that's why if you square root it just to see if it is a perfect square already, you might save yourself some time. So there's actually a cool thing we do with our equals sign to show that this is a rounded number. We make it squiggly to say 3 square roots of 13, which is approximately 10.82. So if you've ever seen those a squiggly equal sign and not known what it was, there you go. So that's our answer, 3 square roots of 13, which is about 10.82. All right, our next example here, we are not finding the hypotenuse. We know the hypotenuse, but we want to find one of the legs. So it's going to work in a similar way where we're going to label A, B, and C, and we're going to plug it into the Pythagorean theorem, but our process of solving is going to be just a little bit different. So again, it doesn't matter which one of these I call A and B. So since I've got 10 labeled as A, I'll do 10 squared plus L squared equals 12 squared. So let's see, 10 squared is 100, and 12 squared is 144. If you don't know those off the top of your head, that's what a calculator is for. So it'd be nice if you knew them off the top of your head, but you know, maybe it's been a long summer, or maybe you just, you know, sometimes it's hard to think. All right, 144 minus 100 is 44. We're going to square root both sides to get rid of the squared here so that we know that L equals. So square root of 44 gives us a decimal, but we can simplify it by thinking about what multiplies to get 44. And when we do that, we want to think about hopefully some perfect squares that multiply to get 44. And at some point I will have a video purely about simplifying radicals that I will put in the description and hopefully have pop up so that if this is something that you're struggling with, you can get some extra help there. Not sure I have one right now, but at some point that'll happen, I'm sure. So 44 splits into 4 and 11. And that's helpful because I can square root 4 and get 2. Can't square root 11. So our side length here, our leg, is 2 square roots of 11, which I'm going to approximate. When you are approximating it, you might as well put square root of 44 in as opposed to putting in 2 square roots of 11. You can put in both, and then that checks that you actually simplified it right. But it's easier to put in square root of 44, especially if you are, say, using your phone calculator because you were too lazy to get up and get your other calculator. That's, you know, not me. I'm not that lazy. I'm that lazy. So that would be our answer here. I got one more like this for example 4, and then we're going to kind of change it up a little bit and do something different. Alright, here we've got another triangle with a leg missing, and this time our hypotenuse is square root of 29, which may seem like a weird thing to have for a side length. But if you think about it, very few things actually will work out for this right triangle relationship to be perfect squares for all three sides. In fact, it's such a special thing that we call numbers that do that Pythagorean triples. So the majority of numbers, if you just randomly pick numbers to put on a triangle, you'll end up with, after you've picked the first two, the third one will be some sort of a square root radical situation. So it makes sense that here we have a square root. If you think back, we had square root answers on all of these so far, most of these, all of these, I think, so far. So it could be that having a square root as a hypotenuse means that we might have a better chance of that leg being a whole number. But because I made up these numbers, I would say that that's not something you should rely on, because I definitely rolled a die 20 to see what numbers I should pick for this triangle. So to do this, I'm going to put into the Pythagorean theorem L squared plus 4 squared equals square root of 29 squared. Now here's how squaring a square root works. If it's just a single square root without anything else around it, squaring that square root gets rid of the square root and it's just the number underneath. If we had something like 2 square roots of 29, just as a side note, and we tried to square it, we'd have to square the 2 and square the square root of 29 and then multiply those two things together. So keep that in mind if that comes up. But that's not what we have here. So L squared is going to stay L squared. 4 squared is, whoops, it's a plus, is 16, and square root of 29 squared is 29, so we need to subtract the 16 over to this other side. L squared equals 29 minus 16, which is 13, and when we square root that, we get L equals, now the square root of 13 is a prime number, so it does not simplify. So if we are wanting the most simplified radical possible, that is square root of 13. The decimal answer we would get by plugging into our calculator. 13 square root 3.61. So that is our side length. Now as you're going through these, and if you are going and getting the decimal answer, not just the radical answer, you should be able to kind of look back at these and say, okay, that makes sense. So for instance, if I'd forgotten about square rooting and I put a 13 where L is, and I think about what that would mean, well, I might also have to do the step of saying, well, what is the square root of 29? About how big is that number? That number should be a little bit bigger than 5, right? Because square root of 25 is 5. Okay, so if you almost forgot to square root and had 13 as your answer, then by thinking about it in the context of the triangle, you go, well, wait, that's too big of a number for this to work. So hopefully you'd be able to go back and look through your work and see what happened. Same could be true if you just made some sort of mental math error when you were squaring or adding or subtracting or whatever it might be. So it's always good to step back at the end of a problem, say, did I answer the question they asked me? And does my answer actually make sense? So answering those two questions can really help you avoid mistakes or avoid not catching your mistakes. Alright, the other direction that we can go here is we can actually say, if I have 3 numbers, do those 3 numbers work out to give me a right triangle? And remember what I said earlier, that the hypotenuse, the longest side, or the hypotenuse is always the longest side. So as we're playing this in, you're not having to worry about which one of these should be C, because C should be the longest or the biggest number no matter what, because the hypotenuse is always the longest side. So let's just basically plug this in, and I'm just going to plug it in the order it's in, since these are from least to greatest. I'm going to say 3 squared plus 5 squared equals 7 squared, but really what we're doing is we're trying to figure out if that's true. So let's see, 3 squared is 9, and 5 squared is 25, and 7 squared is 49. Let's see, 9 plus 25 is 34. Does that equal 49? No, it doesn't. So we would say that this is not a right triangle. And so you'll notice that I put question marks above my equal sign. That makes me feel better as a math person, that I'm not saying that this is equal, I'm saying I'm trying to figure out if it's equal. And then on that last step where I could tell for sure, I marked through the equal sign to say, okay, 34 does not equal 49. And I think both of those are good strategies to use, so that as you're looking back, you're not like, wait, why did I think this was equal? It lets you know that, oh, I was trying to figure out if it was equal. That's how this problem works. So let's try it with 3, 4, 5. And you may already know about what this is going to end up being. Potential spoiler alert there. So 3 squared plus 4 squared equals 5 squared. Is that a true statement? So we do 9 plus 16. We're asking ourselves, does that equal 25? 9 plus 16 does equal 25. So this is a right triangle. And so I mentioned this earlier, special numbers like this where they are all whole numbers, but they work out to form the sides of a right triangle, are called Pythagorean triples. 3, 4, 5 is one of the most common ones, and it's also cool that you can just like double and triple and so on those numbers, and those will also be Pythagorean triples. There's not a ton of them, so you can kind of have some memorized if that's something that you'd want to do. I mean, to each their own. Like 3, 4, 5 is a Pythagorean triple. 5, 12, and 13 is a Pythagorean triple, I believe. And then basically you just end up with bigger and bigger numbers as you go along. So there are not a ton of them, but there are some out there that are whole numbers that work out to give you right triangles. If you have not already tried one of these 3 on your own, this is a great place to do it. Pause the video, see if you can figure it out yourself, and then start the video back up when you're done, or when you get stuck, so that you can see if you got it right or see where your issue is. Welcome back from your pausing. Okay, so we're going to do 7 squared plus 9 squared equals 15 squared. We're seeing, is that true? And, oh man, 15 squared is a fairly large number. Let's see, 15 squared is 225. Oh, I do not think that this is going to work, because 49 plus 81 is nowhere near as big as 225. That would be 130. And that is not equal, so this is not a right triangle. And in fact, in order for us to find a lot more right triangles with 3 numbers here, we'd have to be willing to experiment with some radicals in the mix to be able to try to get more of them to work out to be right triangles. Now, if you do have a set of 3 numbers that involves radicals and they give you something that's a right triangle, those are not considered Pythagorean triples. A Pythagorean triple is whole numbers, that you have 3 whole numbers that work out to be a right triangle. So just as a side note, that yes, radicals can help us get sides of a right triangle, but that's not the same as being a Pythagorean triple. Thanks so much for watching. I hope that you'll like the video, subscribe if you haven't already, and feel free to check out other videos by me. I love helping you with math. It gives me a kick to get comments from people saying, you know, thanks for helping out or whatever. It also is fine if you don't leave a comment, but I love the idea that I get to help like all sorts of people with math that I've never even met, so that's pretty cool. If you have not already checked out my website, KStevMath.com, it is, you know, floating above my head right now, and also there's a link in the description. This is actually a part of a Precalculus course that I am working through this school year, 2020 to 2021, with a homeschool co-op. So if you are interested in going through that with me, you can head over to my website and check out some details on that. Like I said, link in the description. And happy mathing. Have a great day.